Hey folks, so in this video we're going to go over a basic graph ADT for its representation. So already from this, right, we've already had our little bit of a time and our discussion on what is the graph, right, some of the general ideas and terminology of it. Now, right, we need to have a data structure for it, right? Unless we have a data structure for it, we can't really manipulate it. So we're going to kind of have the same, standard operating procedure as before. We're going to basically create a API that's very generic for representing a graph, and then talk about different ways to actually implement, right? So we'll have two main techniques for doing this. Obviously, right, there's different ways to solve a problem. So yeah. So this is our API over here, right? It's our API slash it's an API for an ADT, I guess is a proper thing to say, right? So here's our API. So let's just take a look and see what we have here. So this is our API. So it's called a graph, right? You can imagine this would really be an interface, right? I mean, it's labeled as a class here, but it's going to be an interface, right, when you do this in practice. Because again, you have different ways to implement it. And so we have, first of all, right, a couple constructors. The first constructor basically is meant to create a graph when you know the number of vertices in it. So it's like, well, give me a graph that has 100 vertices in it. I can do that, right? I can basically create a new graph object, right? New graph data structure that has 100 different nodes in it, right? And in this case, you're literally just creating a graph that looks like this, right? So there's no edges between them. It's just a bunch of different little nodes, right? And they're all just out there, right? And there's, V number of them, right? That's how many vertices you have. So that's what that first constructor is doing. Then you have, right, the second constructor. And the second constructor doesn't really matter to us. What it is for the example code in the book, if you want to basically read in a graph from some sort of input stream, right? So if you have, some text file or whatever, right, that has your graph, in there, right, you can maybe load it. For us, right, it doesn't really matter, so we can kind of skip over that. Then we have, right, is two accessors. So we have our int v and int e. So those are basically our accessors to tell us how many vertices are in this graph, how many edges are in this graph, right? So v and e. And v and e, right, are going to be the common things you see in code in terms of that's how we use to represent the number of those things, right? The number of vertices, the number of edges, right? We'll use v and e to represent those special things. So those are very typical, right? Then we have the ability to add an edge, right? So given I'm looking at a graph, right, I want to be able to connect things. So it's like, well, these two things, right, really need to be connected, or maybe these things really need to be connected, right? Something like that. I need some way to do that. That's what add edge does. So add edge takes two parameters, v and w, and it basically forms that connection, right, between two of these two vertices. And then we're good to go, right? So we're actually populating stuff into our graph. We don't just have a bunch of vertices that are spread out all over the place. We have connections themselves. So the next thing we have, right, is probably going to be the most commonly called thing. Well, I mean, add edge will be called, but it'll only be called at the beginning, right? What's going to be called most often during the runtime? It's going to be the second and last one. It's going to be calling ADJ, right, which is adjacent. So basically, what this is this is a function where I give it a I give it a vertex, right? So I'm like, okay, I want to see vertex 10. Give me the adjacency list on it, right? So basically, who's adjacent to it, right? So what nodes are next to it? So if I have a node 10 and next to it are connected to it, right, are nodes 1, 2, and 3. This function will return to me 1, 2, and 3. So it's a way basically of viewing the neighbors of a node, right? Who's connected directly to this node? And so this is what we'll use all the time because it's the easiest way for us to query our graph data structure to say, are these two connected, right? Well, I'll go to one of them, do .adj, right, do .adjacent, and see whether in that node, right, is that other node that you want to know is connected to it, is it in that adjacency, right? Is it, a neighbor of that node, right? So it's the real easy way, right, we have basically to check to see whether two things are connected. The last thing we have there is kind of a little bit of a, well, it's something we've seen before as toString, right? So just for debugging purposes, we can, of course, print out all the edges and all the nodes, right, and show how they're related, right? Typically, the way this prints out, right, is what we call, is using what we call ordered pair notation. So it's like, well, if I have a graph that looks like this, A, B, C, maybe my toString will then print out something like this, A, B, B, C, right? Two ordered pairs, each of them represent an edge, right? An edge between A and B, and an edge between B and C. And it's kind of just implied somewhere that it goes back and forth both ways. All right, so this is our basic ADT, or / our basic API. So the question here for you guys to think about for a minute is this API enough? Is this enough for me to actually get like real work done, or am I missing any key features? So take 1 second, think about it, and then we'll go over it. So here, right, we're kind of missing some things. To me, I'm missing two main things, right? And you guys may have some other ideas as well. I'll tell you the two that I'm really upset at. Well, first of all, I don't have a delete edge, right? So no delete edge means that I can't undo things, right? So if I add a connection between two things, I can't remove it later. So if I decide to change the prerequisite on 222 and I have that class of classes, I can't remove 205 as a prerequisite, right? It's stuck there forever, right? So that's one thing I would really want, right, is a delete edge. The other thing along the same lines is, of course, delete vertex, right? So my kind of limitation here, right, is that in my constructor, I have to tell the number of vertices that are going to be in this graph. And then after I give it that number, right, it kind of populates them all out. They're going to be there indefinitely, right? So I don't have the ability to go and remove one of them. I have to just deal with whatever is there, right? So I can't expand my graph. So that would be my second thing as well, right? So those to me are kind of the main two issues. There are other issues as well. One of the other issues, which doesn't quite show up in the API directly, but one of the other issues is your vertices have to be one after another, right? They have to be contiguous. So yeah, you set a constructor that says int v, right? And it's like, oh, what you're somehow implying is you can have a vertex label 0, a vertex label 1, a vertex label 2, a vertex label 3, a vertex label 4, a vertex label 5, up until v, right? You're going to have each of those, but you're not allowed, right, to be sparse about it, right? So you can't have a graph that just has node 0, node 4, and node 5. You have to have 2, 3 between them. 1, 2, 3 has to be between them. You can't just pick and choose, right? So I have to have them basically one at a time, right, up until my v, right? That's how my constructor is written. So that's another restriction here. I mean, if I have delete edge, right, then I can delete node, or delete vertex, so I can kind of fix that. But still, that's not something that I really want to deal with. So yeah, these are my main two issues, though. Delete edge, delete vertex. That's what's stopping me from calling this a complete API. But for us, maybe it's a little bit fortunate, though, because then that means that there's perhaps something left for us to do on a homework at some future point in time. All right. So a little bit more about using this API, right? So I have kind of two little mini examples, and this API is really easy to use. It's really easy to use. The first example will be really easy and everything will be fine. The second example will get a nice little discussion out of it. So the first thing, right, is to compute the degree of a vertex. So the degree of a vertex, right, this is another keyword in graph theory, is basically saying how many nodes are connected to this other node, right? So if I have, for example, node A here, and then I have, it's like this, right, B, C, D, the degree of A is 3. The degree of B is 1, the degree of C is 1, the degree of D is 1, right? But the degree of A is 3 because it's connected to 3 things, right? So we're asking how many things are you connected to? That's what is meant by degree. And if we were in a directed graph with those arrows, we'd use terms like in degree and out degree. Here we're undirected, right? It doesn't matter. We're just asking who's next to whoever, so we just say degree and we just count up all the different lines that we see there. So how would I write that using this API? Well, I have the code for that method on the right-hand side. So I have public int degree, graph g, int v, right? Those are the parameters. I take in a graph, I take in a vertex to go examine. So what do? I start basically by creating a variable called degree and set it equal to 0. Because like, well, if I'm going to count the number of things that are next to this, initially they're going to be 0, right? I need to go look at things and start seeing them before I can really count up. So I'll initialize a variable to 0. And then I'll have a loop, and that loop will basically look at the ADJ of v, right? So g is my graph that's out there. V is the vertex I want to look at. So I'm going to the graph and saying, who is adjacent to v, right? Who are the neighbors of v, right? And so this little bit of code here basically returns me something that looks kind of like a list. And what that list contains is all of the vertices, right, that are next to the one that I'm looking at. And so I'll loop over it, right? I'll loop over it, and my loop is basically using w as an iterator variable. And I'll look at each of those contents, right? And I don't really have to do anything with w because I don't care who I'm connected to. I just care that I'm connected to somebody, period. And then I'll do basically degree plus plus, right? So I'll count up the number of times that I see that, right? And so if this code runs, it's basically going to count up 1 for everything in the adjacency list on a particular node that I'm looking at. And of course, once it's done, it returns degrees, and we're good to go, okay? So that one, pretty straightforward. Let's look at the next one. Next one's going to be a little bit more tricky. Count the number of self-loops in a graph. So this one, the problem is going to be over here, okay? And we'll get to that. We can look at it, right? So it takes, basically it's called number of self-loops, graph G. Takes in the graph, right? It just wants to return the number of nodes that have a self-loop on it. So basically we have a variable, count up how many self-loops we've seen. And then what we do is we start looping over every single node in my graph, right? So that's what this loop here is doing. It's looking at every single node, every single vertex in my graph. Now, as it looks at every single node or vertex in my graph, what it's then going to do is look at that node's adjacency list and see, is it on its own adjacency list, right? Am I next to myself, right? Do I have this thing going on, right? And so you can notice here, right, that what we're doing is, so we're going basically using v as an iterator variable. V will be every single variable, every single vertex in the graph. So it's going to go through everything. And then, right, we're basically querying what's next to v, right? The thing next to v is being called w. And then we compare them, right? So we say, is v equal w, right? So are you the same thing as the thing I found in your adjacency list? If they are, then increment by 1, right? And so all this code is pretty good, right? You can imagine it just looping through the graph, looking for things that have reference themselves. And then at the very end, the last line is return count divided by 2. This is a little bit iffy, okay? And the reason is, well, so somehow, right, this is maybe we need to know more about the data structure, is that, so the proper representation for a self loop would be something like this, right? I have A that goes to A. But sometimes the way the data structure is set up, like whenever it wants to add an edge, it's really adding two of them, right? So we had mentioned that we were undirected before, which meant that A is related to B means that C is related, so excuse me, it means that A is related to B implies that B is related to A. Well, because of that, some of the graph data structures basically say that when you tell them, so you tell a graph structure, add an edge between these 2 points, it'll basically add two of them, one going this way, one going the other way, to basically satisfy the undirected part. And so maybe my picture then would somehow look like this for a self loop, right? And that's not good, that's very sketchy, right? I'm basically having two self loops, even though I really should just have one. And so that's what this code is actually seeing. It's seeing that there potentially could be, two in there, right? Because of the way the data structure is set up. And it's, dividing to get us the true number. That's what this is doing, and I have it here because that's what the book supports, but this is not the way you do it, right? You should never have to do this, because this, right, this is relying on the API. And somehow what I'm telling you right now is that this data structure trick of having basically the two things here, right, over here and then over here, that's specific to an implementation. So my API shouldn't be influenced by the implementation, right? That was the idea of an ADT. So it's not really a good idea here. Really, there should be some other fix, right? We shouldn't have to do this divide by 2. Really, in our library, we should basically just be checking. We should be able to directly check, is this a self loop? Count them all up, and then they all count, okay? But because of the way that some of the data structure is implemented, it's not that straightforward. All right, so now we've gone over this, right? We have kind of an idea of, what is it that we need to support in a graph data structure, right? So eventually, right, the hope is, right, is that we have everything represented, and then we can write interesting algorithms that do stuff over them. Well, before we get there, right, the next thing, which is going to be the next few videos, is basically going to be the actual implementation of this, right? So how can we implement this graph ADT? So I will see you guys in those videos.